In this module, we're going to dive into the fascinating world of problem solving by searching. We'll begin with a fundamental problem, navigating a map. Imagine you're given a map, much like the one you see here, and your objective is to find a path from a designated start state, in this case, the city of Arad, to your goal state, which is Bucharest. Our task is to identify the most efficient path between these 2 points. Before we tackle this specific navigation problem, let's explore a few other scenarios where the same underlying search algorithms can be applied. The beauty of the algorithm that we are going to learn is their versatility. A single approach can solve a variety of seemingly different problems. Consider this classic puzzle. You're presented with a start state where numbers are arranged in a grid. Your goal is to strategically move these numbered tiles one by one into the blank space until you reach a predefined goal state. For instance, from the current arrangement, you could move the 6 into the blank space, or slide the 2 downwards, the 5 to the right, or the 3 upwards. At any given state, there's a limited set of actions you can take. Each action leads to a new state, offering further actions. Our ultimate objective is to navigate through this series of states to reach the desired goal. Do you see the similarity between this puzzle and our map navigation problem? In both cases, you start at an initial state, have a set of available actions, and aim to reach a specific goal state by traversing through various intermediate states. The core idea is to search through the state space to find the path to our goal. Although they appear different on the surface, these problems share a common structure that allows us to use similar solution approaches. Let's look at another example, the 8 queens problem. Here we have a standard chessboard, and the challenge is to place 8 queens on it in such a way that no 2 queens can attack each other. Remember, queens attack horizontally, vertically, and diagonally. The configuration you see now is not a solution because some queens are attacking each other. Our task is to find a valid arrangement by moving the queens. This problem is remarkably similar to the previous ones. We start with an initial arrangement, and our actions involve moving queens to new positions, generating new states, until we reach a final state where no 2 queens are in an attacking position. Finally, let's consider a simpler called the vacuum world. Imagine 2 rooms, Room A and Room B, both potentially containing dirt. Your intelligent agent, a vacuum cleaner, has the objective of cleaning both rooms. Similar to the other problems, the agent has a limited set of actions. It can move left, move right, or clean the current room. From a given state, e.g., vacuum in Room A, dirt in both, the agent might choose to clean Room A, leading to a new state where Room A is clean. Then it might move to Room B, creating another new state. The goal is to reach a state where both rooms are clean. We're looking for the most efficient sequence of actions to go from the initial dirty state to the final clean state. While the agent could inefficiently cycle between states, our aim is to find the optimal path NA as you can see. The algorithms we'll discuss for the map navigation problem are applicable to a wide array of problems, including puzzles, strategic games, and even robotic tasks. To effectively solve these diverse problems using a unified approach, we need to standardize their formulation. This means describing any problem that involves searching using a consistent set of 5 key components. By doing so, we can then apply a standard algorithm to find the solution. The first component is the initial state. This defines the starting point of our problem. For the navigation problem, it's our current city Arad. For the puzzle, it's the initial arrangement of the tiles. Next, we define the actions available to our agent. These are the possible moves or operations the agent can perform from any given state. In the navigation problem, the actions are moving to a neighboring city. For the puzzle, it's sliding a tile into the blank space. More formally, we'll assume the existence of an actions function. This function takes a state S as input and returns a list of all available actions from that state. For example, from Arad, the actions function would return a list containing go to Zerind, go to Cebu, and go to Timisoara. In the puzzle, it would return actions like move 5 right, move 2 down, and so on. We'll use square brackets to denote a list of actions. The third component is the transition model, which tells the agent what state it will reach if it takes a particular action from a given state. We'll define a result function for this. The result function takes a state S and an action A as input, and it returns the resultant state S dash after applying that action. For instance, if the agent is in Arad and takes the action go to Zerind, the result function would tell it that the new state is Zerind. In the puzzle, if the agent is in a particular tile arrangement and chooses to move the 5 to the right, the result function would return the new arrangement of tiles. The fourth crucial component is the goal test. This is a Boolean function, meaning it returns either true or false, that determines whether a given state is our desired goal state. The goal test function takes a state S as input. If S is the goal state, it returns true. Otherwise, it returns false. For our navigation problem, the goal test would check if the current city is Bucharest. In the puzzle, it would verify if the tiles are in their target configuration. Finally, the fifth component is the path cost. This quantifies the cost associated with taking a particular action. For example, in the navigation problem, the cost of moving from Arad to Zerind might be 75 units, representing distance or time. In the puzzle, we might assign a uniform cost of 1 to every tile movement, meaning each action costs the same regardless of which tile is moved. The path cost function tells us the cost of transitioning from one state to another via a specific action. So to summarize, for any problem we want to solve using search, we need to provide the agent with these 5 pieces of information: the initial state, the available actions, the transition model, the goal test, and the path cost. With these defined, the agent's task is to analyze this information and generate a solution, which will be a sequence of actions that leads from the initial state to the goal state.